Okay. Hi guys. Today we will talk about, I think, a very important topic which I never covered in my channel, which is the PFC. So let's start with this slide first. So whenever you have in this side the AC grid, in which case is called AC mains, you're gonna have a sinusoidal waveform. And if you want to have a DC here, your first approach would be to use a full bridge rectifier, like this. This is a passive full bridge rectifier, and what it does is that when there is the positive, two diodes are on, and you will have this. And when the negative, instead, when there is the negative sign, the other two diodes will be off, and the other will be active, making it another positive waveform here. And with the output filter, which can be just a capacitor but also an LC, you're gonna have a DC with a ripple. It is more zoomed here because this ripple here will be given by the capacitor voltage. This is the ripple voltage, and this is the capacitor current, which, specifically speaking, you're gonna provide at each time here. So this is the charge. The area under this is the charge Q, which you have to provide to charge your capacitor. And so in the other time you are discharging the capacitor, creating a ripple. But this is not the correct way to have a DC waveform, because when the power is very high, let's assume that the power is greater than 1 kilowatt, distortion will happen, like this. And so, to avoid this distortion, I don't want to bother you with all the math. There is all the demonstration that you want, all the mathematical proof that you want. I don't want to bother with you these things. I am here to simulate, to make you understand that there are some limits. If you want to design some powerful circuit having the grid at the input, you have to respect these limits here. Otherwise, distortion will happen. You will have a lot of unused power. So what the PFC does is to optimize all the power and to correct this harmonic distortion. The PFC is basically most of the time is a boost. So this is a boost. This is inductor L, this is the diode D, and this is the switch Q1. This is C, the capacitor, output capacitor CO. As you can see, there is no input capacitor CI. This is very important because you save one capacitor from the input side. What the difficult part of this will be the boost control, but nowadays there are more integrated control, and so you can import something in LTSPICE and make it simulate to make you understand the work. But by the way, you can also design the boost control by yourself. It will be quite a challenge, but you can do it. These are the two waveforms. This when performing in CCM. Pay attention that the boost in CCM has the famous right hand 0, right plane 0. So normally speaking, when the boost works in CCM, it's very hard to compensate. But in this case, when it works as a PFC, you can design, since at the input you're gonna have another design boost, especially here in this case. So this is the CCM and this is the CRM condition, because the inductor current touches the 0 here. So it is not a DCM, it is a CRM. It's different. So you always have T off and T on, so you don't have the waveform of the DC, which is very ugly, because here in this interval here you're wasting energy. You just have CCM or CRM condition. Basically, the control will read the polarity, as you can see here, and the boost converter, and it will make the duty cycle of this guy switching accordingly. You will see everything in the simulation. Now, this is an example of this is the MP4040010. This is an example of PFC controller. How does it work? Our circuit will be very similar. It is not this integrated that we will be using. It is another one, but the concept is the same. You have the input AC here. Then you use a Gral's bridge here. Then what you do is first you have to supply this guy. How you can do that? You have two ways. You can either use this circuit here. Basically, you take the main inductor, you couple the main inductor with another inductor, you reduce with a ratio MP over NS. After that, you use a voltage double, and here you terminate everything with a peak detector, making more or less 12 volts. Or you can directly use the main inductor without coupling, and you basically do the same. Plus, you can also add a zener to protect the input voltage. Or you can do like this guy did. Basically, this is let's call this first method, and let's call this second method. This guy here used the first method because, as you can see, he took the main inductor, and then with D3 is a zener, D2 plus C3. D2 plus C3 makes a peak detector to have a DC voltage here. It is useful when you have to provide just a few amps, like 100 milliamps or even less. Then you have to also, to compensate, you take the divider here from the output voltage, and then you have to make the compensation ramp. Since this is a current control, because as you can see, there is a rate which is the current source compensator. You have to provide a type 2 compensator. The type 2 compensator is an RC with a C here. I discussed here in another video. And yeah, basically that's it. So that's how you design all the circuitry around the boost. Now what we will be using is that we use the LT1249, which is already in LTSPICE. This is the block diagram, but the concept remains the same. At the output here, like explained in most of the videos, you have a follower meter class B amplifier to give more current to the switch. Then M out is an important pin, which basically is used as the multiplier. So the multiplier current goes inside this M out. You have the Gral's bridge, and you have just a resistor. 200 milliohm can be enough. You use this voltage here to generate the reference voltage of the current loop. This is the error amplifier, which is important for the control. And all of this circuit is basically the compensation ramp, as you can see here, and the oscillator, the clock, everything that you need. But this is just a block diagram. So now let's use LTSPICE, and let's see this guy, LV1249, power factor controller. So let's do this. Let's put the ground to the ground. This is very important to do. And let's design first the boost. So let's use a very high inductor, and let's use a MOSFET. Let's pick a reasonable MOSFET, for instance, with low gate charge and low RDS resistance. So let me pick this one. This can be very good. Now you always need to limit the signal from the gate with a resistor. Let's put 1 ohm for starters, and of course let's connect it to the ground. Then there is also the boost. Let us put a very high inductor, and let's put a Schottky diode here, because it is faster and it has less drop. let's connect like this, so that we have the boost converter. And now you have to sense the circuit. Now I have already made the calculation for you. You have to design a here you have to design a divider, basically, to read the output voltage. Let's put 20 kilo ohm like the macro model does, and 1 mega ohm. So in this case you are basically putting all the output voltage inside. Let's put the output capacitor, but we can save space here. Let's stay optimize. Okay, this is enough. And let's put the output capacitor of 12 micro. Let us put a Kemet X7R with a great voltage. Okay, we put a word. This maybe has a bigger ESR. Yes, it is a bigger ESR. So let's put another one. Let's put another one to reduce it, to reduce the ESR. Maybe 3 of them should be enough. Okay, no, so now the ESR is reduced, but the inrush current has increased. Let's put a light load with 2 kilo ohms. And let's call this node out, because it will be our output voltage. We needed to design also the compensation network from here. So we take the output voltage from the sense, and we connect to the output, and we connect to the compensator by putting a two-type compensator network. As you remember, the type 2 compensator is a RC resistor. So let's put the RC resistor. We will start by the suggested one by the datasheet, like this. The datasheet suggests a value of 303 kilo ohms and 0.047 micro, and the same from this. These are suggested by this value are suggested by datasheet. So we will start doing like something like this, and let's see. By datasheet, and let's connect like this. Now let's connect this with 1 mega ohm resistor. I don't think that you don't even need to do that, because because the controller here needs the controller from the other part. So let's put a line, draw line here. This line here divides the circuit from the DC. Okay, so this is the DC part, and the AC on this side. Let's put just here. Let's put just 10 volts, 12 volts. As I said, you should design the circuit here, but you can directly put 12 volts. And for the CEA is the current amplifier, and we need the compensator. Sorry, I said something which is not very true. The compensation ramp is here, and as a type 2, you will need to put as always the RC, like this. So let me prolong the ground like this. This is 100 pico, 10 pico, 10 kilom, and 100 pico. Remember that when you design a type 2, generally speaking, the capacitor here is very low. This capacitor here in particular, because what you have to create, basically what you have to do is to create a transfer function which is like this. And so the 10 pico will mainly act here, and the other, which should be something around the nano, will act around here. So now let's use the sinus voltage from the AC side, and as you know, you will need the grals. So let's put the 4 diodes. Like this. So these two are used for the positive, and these two for the negative. And you can connect the grals like this. Or if you want, you can do the grals horizontally if you are able. You can do that, by the way. And so you can connect everything like this. Now you need to read this current here. And the way to do that... Sorry, first let's connect this to this. You need to connect... you need to read the current here. This is not good. Okay, you need to read the current here. So the way to do that is to put a low side shunt. Let me put a low side shunt right there with 200 million, and yeah, let's connect, and let's connect it to here. Let me cancel this because it's occupying some space. Let me reduce the line here, and everything should be good. Let's put a sine wave between with 0, 165 and I don't know, 600 hertz. So everything should be good. The ground is just 1, and we have the separation between the AC and DC. Let me save the file as PFC, and let's run the simulation for... sorry, I have to charge the output capacitor, otherwise the transient will be quite long. So let me write .ic vout equal to 385. Now the capacitor will start already charged, and so by skipping the skipping is a point solution for 20 micro, yes, it was correct, 20 micro, and skipping the initial operating solution, Can't find the model C. Did I forgot? Okay, probably I forgot to. Ooh. Ah, sorry. This is just a bypass capacitor. Don't. Let's put 170 pico. I forgot. I completely forgot. So now, let's see what is going to happen. We will first analyze, of course, the input voltage, which is a sine wave, like you expect it to be. Then we'll analyze this node voltage here. As you can see, there is some noise. There is quite the noise. You know why? Because it is switching. And if we see this node voltage here, it is switching properly. Now let's see the inductor waveform. Please don't crash. Please don't crash. Please don't crash. Please don't crash. Of course, it is the opposite. So, what is going on? Basically, at the beginning, there was the inrush current. There is a very high ringing. I can't understand nothing. I honestly can't understand nothing. Let's close the simulation because I have to name these nodes, because otherwise really I can't understand nothing. Let's call this V switch, and let's call this okay, V switch, V out, and let's call this V in DC, and let's put this is programmed just for 10 milliseconds, and so let's put 10 milliseconds. Now let's run the simulation, and finally we can see what is going on. So let's see the switching waveform. Let's see the inductor current, which is, as you can see, following exactly what we were expecting on the paint. As you can see, the inductor current has really this waveform here, and at the beginning there is the inrush current caused by the fact that these capacitors here are still to be charged, even though I put the so let's just focus on this one. Let me put a minus here. Okay, so that's the waveform that you are seeing. This is in CRM condition. So as you can see, you have two kind of ripple. The first ripple is given by the fact that the AC waveform is changing by the rectifier. If I put here, you see that the ripple is given exactly by the red waveform, which is the rectified waveform of the input. Now, what we wanted to see is how the gate here is behaving. This is very important because okay, so it is behaving correctly. So we designed correctly the resistor, and there is no ringing. This is also very important to see. Now let's increase the load. So basically, that's a PFC. You see that there is the first ripple at the given by the rectified current. What we can also see is the Fourier analysis. To do that, so by as you can see, by decreasing the load, there is still a bit of CCM here. And if we see the output voltage, it is a very clean. I'm kidding. It is not clean, but yes, yes, it is. It is acceptable. It is yeah. It is acceptable. It is acceptable. A PFC is very noisy, so it is acceptable. If you want to do that, you can also use the statement dot 4, which can analyze the distortion factor. Just write dot 4 here with the output voltage V out. But more than that, I would like to use the ending transient. So between 9 milliohm and 10 milliohm, just this part here, to analyze so when the transient has ended, to analyze the Fourier transform. By doing that, you can see also the components of the output voltage, and you will see that it has two components. It has actually two components. The components given by the switching frequency and the other by the rectification. Now, if we wait patiently, we will see that. Okay, so let's use the let's view the FFT of the output voltage, and let's put the linear one. It is not scaled. Auto range. It doesn't work. Why it doesn't? Let's put 100 volts. Even less than that. Let's put 10 volts. One hertz. It is bugged. So as you can see here, there is also the left component given by the. I don't know why it is so bugged, but it doesn't matter. The thing is that here at 100 kHz, you have the switching frequency component, and as you can see, it is not that high. Should be higher though, but I don't see anything on the spectre. But it is this 100 kHz. Oh, now you can see also the replica. You can see also the replicas of 200 kHz should be here. Yes. So this is the first harmonic, second harmonic, third harmonic, and so on, given by the ripple. The ripple of the converter. If you do now analyze this view FFT of the inductor current, you will see that you're gonna have always components which are not belonging to the switching frequency. So the concept is the same. As you can see, you have the ripple given by the switching frequency, because the inductor is because it is the inductor, so it is normal to have these components so high. But then there is also a component in the 60 Hz. So if I put, I don't know why it doesn't work, but it should. It doesn't. I don't know why. 1. I said 1. Ah, thank you. Finally. So now you can see it. That there is the ripple also in the other side. Well, I think that we can close everything here. We have successfully simulated the PFC, and I think that we can close everything here for today. Thank you guys, and see you in the next video.